This presentation is delivered by the Stanford Center for Professional Development.
Okay, hi everyone. I'll get started again for cs224n. Okay, so today's the final lecture on machine translation, and so today I plan to tell you everything else there is to know about machine translation. Well, I can't exactly do that, but I guess I sort of more want to then concentrate on the sort of main additional ideas and do something of a survey that gets up to what's currently basically the state of the art of what people do for statistical machine translation systems. And an interesting thing that we'll come to in a little bit is these IBM models that we're looking at, they actually are still used in state-of-the-art machine translation systems, though they're not the whole system. They're actually used now as a component in how those systems are built. So first of all, I want to quickly finish going through the hierarchy of IBM systems, and then I want to talk about evaluating MT systems, because that's in general important to know how you have a good one, and also comes up in the assignment, and then talk about some of the modern ideas in statistical phrase-based MT systems and syntax-based MT systems. Okay, and so just on the other announcements, don't forget today's when the first assignment is due, and also today we've got the second assignment coming out, which is then the statistical MT alignment models, which you can put together with your language model to have a little MT system. And then on Friday, the section is going to be talking about the kind of EM algorithms that you need to implement for the assignment. Okay, so we spent a lot of time on IBM Model 1, and so at a high level, the important thing to think about is that essentially the only information that this uses as an alignment model to translate words is it's trying to learn these probabilities of how to translate an English word into a French word, right? That's all it's got. All other knowledge of language has completely disappeared. So it doesn't have any ideas about knowing about phrase structure. It doesn't know that words at the start of the sentence will probably be translated near the start of the sentence. I mean, it literally knows nothing else. So in some sense, its character is very like a 1950s machine translation system where the way you translate is you come to the next word, you look up in the dictionary the possible translations, and the only difference is we have a probability distribution over possible translations rather than just a list in the dictionary. I mean, in particular, as a question for these guys, so words, lots of words, as we've discussed, have lots of meanings. So the most famous word ambiguity in English that everyone uses as their first example is bank, which can mean either the edge of a river or a financial institution. And so when we want to translate that into French, those two meanings of bank get translated differently. So if we build a Model 1, actually I should be doing it the other way. I should be choosing a French word that has two meanings in English, actually. So if we're doing French to English machine translation, if we're taking a French word that has two possible translations in English, if we're building a Model 1 model, can these alignment probabilities help us choose which translation is appropriate in a certain context? Yeah. No. Okay, yeah. So these alignment probabilities are completely context-free. All they know is marginal statistics. They know what the most common translation of that word is and the second most common translation. Okay, but nevertheless, if we're building a French to English machine translation system using the noisy channel model, have we got a chance of getting that right? And if so, how? Right. Yeah, so our language, yes. So the answer is our language model. So at the moment, our whole system is built on this leap of faith that essentially our language model can save us. So the hope is that all the alignment model knows is the more and less common with probabilities translations for an individual word. And so it'll just sort of suggest those as possible translations. And then we just pray mightily that when the language model comes along, it will save us and it will propose appropriate translations in context. And you know, sometimes that's actually going to work. So that if you have something where there's a good context, like if you have a word, I mean, a lot of the time you can get context for disambiguation by looking at what precedes. So that if you have some kind of collocation like riverbank, right, the fact that the river is the word before gives a lot of context as to what sense of the word follows. And so that context will go through the translation. And so the language model will prefer to put together words that have kind of good mutual collocational information that fit together well with each other. So quite a bit of the time, you can actually choose appropriate translations by having the language model do all the work. On the other hand, if you start thinking to yourself, boy, you're really hoping for a lot there, that can't work all the time, you'd be absolutely right. It absolutely doesn't work all the time. Okay, so then if we head up the IBM models, I mean, essentially, you know, the models get a ton more complex, but really they only put in 3 very simple linguistic ideas that they try to capture. So there's just this sort of this minute bit of knowledge of how languages work that gets added as you go up the models. So the first bit that I talked about last time was when we went to model 2, we have this idea of displacement, which is, by and large, the words at the beginning should appear at the beginning of the translation, and by and large, the words at the end should occur at the end of the translation. That's pretty crude, but it's a little bit true, and that gives us some value. Okay, and so then today I want to go on to the next 3 models, which add in a couple more ideas. I'll just mention at this point, in current practice, and you see this in the Draftsky-Martin book, after Model 2, people normally intersperse what's called the HMM alignment model, and that's discussed in the Draftsky-Martin chapter. It wasn't an original IBM model, and I'm not going to present it here right now, mainly because, well, since we haven't talked about HMMs at all, that'd be a big digression. But in practice, people have found it a useful model to stick into the hierarchy there. Okay, so if we go on to Model 3, the big idea that we want to capture here is when we're doing these word alignments, that what we were doing is that we were just going through each position. So we were saying, okay, let's go through each position and let's have an alignment variable that gives the source for that position. And so there was nothing in our assigning alignment variables that stopped us aligning every word to one word, right? That the alignment variables are independent of each other. And so that in part is a very good thing. Keeping the alignment variables independent of each other means that you can train models 1 and 2 very efficiently. And it's precisely for that reason that we only do models 1 and 2 in the assignment. Because if you want to start having complex dependencies between things suddenly get a lot more complicated. In fact, you'll find in the text of the second assignment, when it suggests things that you could do for extra work, one of the suggestions, in fact, I think it's the first suggestion, is you could try implementing Model 3. As a little warning, no one who has attempted that has ever succeeded in getting it to work in the length of the time you have to do assignment 2. So unless you're really, really feeling gung-ho, you'd probably be better off ignoring that suggestion and looking at the other suggestions of ways in which you might be able to make things better. Okay, but at any rate, the idea that, what we could do is just say that every every word could be aligned to the same word. That's clearly linguistically ridiculous. In particular, there should be a kind of an idea that, a lot of the time words do translate one-to-one, proposal to proposition, right? That one-to-one is common. On the other hand, depending on the language pair, there are just regular cases there'll be exceptions to that. So in French, not, at least in written French, is standardly turned into this ne pas, which surrounds the verb. So you'd actually expect the word not to have a fertility of 2 when going from English to Spanish. And similarly here, implemented is being translated by this sort of put in implementation little phrase. So implemented has a fertility of 3, that it chooses 3 words in the translation. So we should actually be able to do a better job at aligning words if we'd actually learnt some information about the fertility of different words, because then we'd kind of know appropriate ways to do the alignments for them. And so that's precisely what's in Model 3. And so this is a picture of what Model 3 looks like. So Model 3 is again being done as a generative probabilistic model. And it's a much more complex generative process. So what we're wanting to do is come up with an estimate of the probability of F given E, just like before. And the way we do that is if we start off with an English sentence, we first of all have a fertility for each word, where the fertility is a probability distribution over different fertilities. So if we think of it as a generative model, we roll our dice, and based on the fertility of each word, we work out that it's going to become some number of words in the other language. And I'm indicating that here just by replicating the word. So did when we rolled the dice, it said its fertility is 0, so we just have it go to nothing. But slap, we rolled the dice, its fertility was 3, and so I've now produced three copies of the word slap. Okay, then we still need to have words in the output that had no source in the input, the spurious words. And so we have a second probability, which is a probability of between each word sticking in one or more null words. So we stick in one null word here. Okay, and then at that point, we then have a translation model, which is like what we had in Model 1. So this is the equivalent of the probability of F given E in Model 1, where we're just doing a single word-for-word translation, which turns our English words into here Spanish words. Okay, and then finally, we still want to keep what we inserted into Model 2, and so we also have a displacement model, and the displacement model is telling us the probabilities of these words being displaced relative to their position in English. And so that will reorder the sentence, and that will give us our output. So effectively, this is just a considerably more complex model where we now have a bunch of probability distributions. So we have fertilities for a word, and again, there are strong independence assumptions in this model. So fertility of a word just depends on what the word is, doesn't depend on other fertilities or surrounding words. And then we have the translations of a word, which, was still just like what I was complaining about. They're still just being done independently, so we're still relying on the language model to save us. And then we have these displacement probabilities, which are just like Model 2. So again, there are huge independence assumptions there. So displacement is just how likely words are to move how far around. It's not specific on what the words are. Okay, and so that's kind of what you're seeing here. So the translation probabilities, chances of putting in extra word for the translation, where that R is the Spanish R, not the English R, fertilities of words, and then distortions. So these are the kind of distortions that you'll want to have in Model 2 for the assignment. So distortion 5.2 is the probability that the English word and position 2 of the English sentence generates the French word in position 5 of the French translation, where formally you want to have that conditioned on the lengths of the 2 sentences, where you've generated a length for the output sentence, so you get a well-formed probability distribution. Yes? So you can rely on the language model. You can hope dearly that the language model will do everything, and that's what Model 1 does. And to some extent, yes, since the language model will want to keep words in good orders, to some extent that will capture what the distortion model does. So you could hope that even though your Spanish starts off with the order of article, noun, adjective, that when you translate it into English, the English language model will know that adjectives don't come after the noun in English, and so it will just move it around and say, no, it'd be much better if you produced article, adjective, noun. Yes, and that may work for you. But, I mean, there are crucially a lot of circumstances that it won't work. I mean, a kind of obvious one is if you take a sentence like, you know, a dog bit a man or something like that, and you, well, actually, I want to go with the opposite of the man biting the dog, right? So the man bit the dog is the actual source sentence, okay? If you then translate it without any knowledge of distortions, and you have a really good language model, the really good language model is just looking at the words that you're offering it, and it's going to say, man biting dog, that's kind of really rare. Dog biting man, that's pretty frequent. Let's move those around, and look, I get a much better language model score, so let's go with that one. And that would be wrong, right, because we've lost the semantics. And if in that case you had a distortion model, the distortion model, fingers crossed, might encourage you to get an output which was still the man bit the dog. You know, there's a lot of keeping your fingers crossed there, because you could imagine it going wrong in various ways. But that at least kind of indicates why distortions might be useful on top of the language model. Okay. Okay. And this is just a little fine point. I mean, that on the distortions, you could kind of have the nulls inside the distortion probabilities for generating spurious words. But in practice, people don't normally do that, and the spurious words are just put in the positions that aren't claimed by the real words, because really they don't have a position in the source sentence themselves. I mean, in particular, you kind of don't really want to say that the source for all the spurious words is at position 0 at the left end of the sentence, because that would mean that most of the spurious words would have huge distortion penalties, where really they shouldn't have distortion penalties at all, because you're just inserting them in places in the sentence that are grammatically appropriate. Okay. That's another slide going through Model 3, but maybe I've had enough Model 3 at that point. And so really at the high level, the essential thing to have in your head is just there's this one new idea. We're modeling how many words an English word is typically translated by, and that will give us better translations, because we won't be able to get these funny alignments where multiple words align to one word. And you know, that's something you probably shouldn't build Model 3, but that's something that you should look out for when you're looking at the output of your Model 1 and Model 2. I mean, to digress for a moment on the day that the first assignment is due, in the assignments it has this discussion of how we like people to do some error analysis and look at the output and think about it and say some pertinent things about it. And we really do, right? That what we'd like not really is just that your write-ups are as long as possible by kind of dumping out lots of junk of probability tables or something, but that your assignments rather appear to have had some mental energy that went into the write-up, and the mental energy is really in looking at what it does and being thoughtful about it relative to kind of what you'd like to have a system to do. So for this machine translation case, one thing that you could do is look at the alignments your system is getting. Do you see obvious places in which multiple, 3 or 4 words are being aligned to a single word inappropriately, which are just the kind of thing that Model 3 is meant to fix? You don't actually have to write Model 3. You can nevertheless, in your write-up, show a couple of examples of that and sort of point out that this problem is indeed occurring with your Model 2, and therefore you kind of understand better now why Model 3 perhaps is a useful thing to have around. Okay, how do you learn Model 3? I mean, the short version is in exactly the same way you run EM. The long version is that, boy, it gets a lot more complicated. So we still start off with the same parallel sentences, and so we still, just like for the other EM algorithm, we just give some values to all of these parameters, and then what we're going to do is, based on those parameters, find likely alignments. Then based on those likely alignments, we're going to re-estimate all the parameters, because once we have likely alignments, I mean, we can just look at the fertilities, right? If a word has been aligned to 3 things, we say fertility 3, and, put that into our counts and run the EM algorithm. So, at a very high level, it's exactly the same, and it's not really any more complex. At an implementation level, it becomes a ton more complex. And the reason for that, I'm going to kind of just gloss over here, but it's really an important thing that you should think about and understand. And for doing that, you should be looking at Kevin Knight's MT tutorial and in the Draftsky-Martin chapter 25. But, the high-level point is if you're doing Model 3, precisely because you've put fertility into the picture, that alignments are no longer independent, right? Because whether one alignment exists affects the probability of whether another alignment to the same word exists, because you've got a fertility factor in there. And so the fact that you've lost that independence assumption between alignments means that it's very hard to explore the space of alignments and work out the probabilities of different outputs. And in fact, in practice, people use various kinds of heuristic search procedures. Whereas in models 1 and 2, precisely because alignments are independent, that putting in one alignment makes no difference to the probability of another alignment. And it's precisely because of that that you can kind of ignore everything that goes around you and just kind of work out expectations for individual alignments, as I showed in that slide for Model 1 and said, just implement this and it'll work. But I really encourage you to actually sort of read through Kevin Knight's tutorial and or the Draftsky-Martin and actually kind of understand what assumptions you have to make to get that to work and why it breaks down for Model 3. Okay, so then we go on to Model 4. And I mean, Model 4 is perhaps best illustrated by this picture. So here we have a French and English sentence. So the English is, on Tuesday, November the 4th, earthquakes rock Japan once again. Now what happens when we translate into French? Well, we have a word with a fertility of 4 here, because earthquakes is being translated by des tremblements de terre, so the trembling of the earth. Okay, so that's kind of cool. Have been newly rocking Japan. But the bit I want to focus on right now is right here at the beginning we have on Tuesday, November the 4th, and in the French translation it appeared right down here, Tuesday, 4 November. Okay, so what happened was that this temporal modifier moved right from the beginning of the sentence to right at the end of the sentence. And to some extent, that's just a choice that sort of doesn't even mean a lot. Because, I mean, the English sentence could have been, earthquakes rock Japan once again on Tuesday, November the 4th. But nevertheless, there are kind of slight preferences between languages, and in English, people more commonly put those kind of temporal modifiers at the beginning, and in French, they're more commonly put late in the sentence. At any rate, this was the way the translation was done. Okay, well, if you're wanting to learn this as the correct alignment, and you're using Model 2, you're kind of going to be in big trouble, because if we look at these alignments, they're all going to involve huge displacement penalties, because this word has a huge displacement penalty, this word has a huge displacement penalty, that word has a huge displacement penalty. And that kind of seems unfair, because really what we have is this one phrase that is expressing the date that's moving from the start of the sentence to the end of the sentence. And well, one appropriate way to start thinking about this is, gee, we need to build models that actually have some phrase structure in them, so they know about the structures of phrases and languages, and we can model things that way. And that indeed has become an extremely popular topic in recent work in statistical machine translation that I'll mention in the end bit of the class. But IBM Model 4 did something simpler, and what it did was essentially just to handle these cases by saying you should only be penalized badly once. So when we align Tuesday and Mehdi here, you're going to be penalized for there being a big displacement. But when you're then considering the alignment of 4, the alignment of 4 displacement can be calculated relative to the preceding word. And so therefore, here you'd say, well, there's no displacement because it's gone along with the previous word. And this one has no displacement. Oh, actually, sorry, these two are swapped, so I guess there is a displacement of 1. But anyway, there's a small displacement here and a small displacement there, and so you only get small displacement penalties because you can base the size of the displacement on the previous word. And so that kind of simulates saying that it's roughly okay to move whole phrases, that you just get penalized once for moving the entire phrase. Okay. And then the difference between IBM Model 4 and Model 5 is purely technical, and so I'm really not going to dwell on it. So the way they did IBM Model 4, the model was deficient, which means that it didn't actually give a probability mass of 1 to possible alignments. Some of the probability mass was lost on illegal alignments. And so on Model 5, they did a bit more hard work, and they managed to come up with a way to have a non-deficient probability model. But that's purely technical. Okay, so one final question that it's just good to have a sense of is, well, why do we have all of these models 1 to 5? I mean, of course you could think, well, this is just an historical recapitulation. They invented Model 1 first and saw how that worked and decided it wasn't very good, so then they built Model 2, which was a bit better, and kept on going. And, you know, in some sense, that's probably true as to what they did. But it's not really capturing why people still talk about all of these models. And the answer for that is that people actually still use most of these models. I mean, sometimes they don't use all of them, but they at least use most of them. So, you know, maybe in the current system, the kind of thing people might commonly do for starting off building models is they'll run Model 1, you know, they might skip Model 2 but use the HMM model, and then they'll run Model 3, and then they'll run Model 4, you know, something like that. They really run a bunch of these models. And the reason that they do it is effectively having the simple models is a very effective way to bootstrap the more complex models. And, you know, in sort of the flavor of things is something like kind of doing some kind of annealing process. So that the idea is, for the high order models, they have a ton of parameters. And if you just directly try and train those models, you get a minor bad effect, which is it's really slow to train the models. And you get a major bad effect, which is since you're trying to do EM optimization in this highly non-convex space, that you very easily get stuck in bad local maxima and you come out with a very bad model. So instead of that, what you can do is first of all train Model 1. And so Model 1 you can train really fast. because there's no search over alignments. And you can get out of it sort of, you know, Model 1 isn't a bad space to search over, so you can find decent models to the extent you can relative to Model 1. And so you can precisely use those models to initialize Model 2. And so that will mean that the Model 2 parameters will already sort of start off in a sensible part of the probability space. And then you repeat that over. So you train Model 2, and then you can use the Model 2 parameters to initialize Model 3. And so that means in the very first round of EM estimation of Model 3, rather than it being like when we did Model 1, where all you were doing was counting sentence co-occurrence and getting out who knows what for things like fertility probabilities, that your first estimates of your fertility probabilities in Model 3 are based on the alignments that you found with Model 2. So they're hopefully already halfway reasonable, and you kind of hope to kind of ride a wave in the good part of the optimization space and find a good model. Yeah?
By the time you iterate up to Model 5, do you just use Model 5, or do you use some sort of interpolation between the 5 models?
Normally, people just use the final model. Yeah. I mean, you know, that's certainly an idea that you could think of trying, but in practice, people don't do that. I guess I actually feel I don't know for sure that there's no value in that. I can't think of anyone who actually tried that and reported that it worked either better or worse. So I don't actually know an answer for that. But clearly, you know, that kind of interpolating simpler models is something that's been used to good effect in other contexts. So you can imagine it actually working to do that. Yeah, I know. That's a good idea. Okay. Yeah, but then on the final note on alignment models, it is important, you know, in some sense they end up with these big, complex probabilistic models. I mean, at the time that IBM first proposed these models, which was in the early 90s, you know, the models were so complex that essentially only someone with the resources of IBM could actually build models like Model 4 and Model 5. I mean, fortunately, in the intervening 15 years, computers have become way, way, way cheaper and faster. And these days, you know, anybody who has, you know, a dozen Pentiums can train these models up in a fairly short amount of time. So that's good for the field. But, you know, it's important not to be lost in the complexity, to not realize that there's still just very little knowledge of language in these models. So, you know, here's this simple fact about French or Spanish, that in French or Spanish, adjectives normally come after the noun, and in English, they basically always come before the noun. You'd kind of like to know that. You'd kind of like your machine translation model to know facts like that you need to reorder adjectives and nouns when you translate between the languages. And so it's crucial to realize that there's just nothing in these models still that can actually capture facts at that level of generality. All we can learn is that displacements of one in either direction seem to turn up kind of commonly between these language pairs. But displacements are global parameters. They don't know about the part of speech of words or anything like that. That's obviously a suggestion of something that you could do to try and improve these models. If you knew the parts of speech of the input and you learned part of speech specific distortion parameters, would that help? I mean, I think it would. I mean, that's the kind of thing that you could try. So really here, though, we're only relying on the language model to try and fix things up. Okay. Okay, so now I skip on to the next lot of slides. Okay, so the next thing I should say a little bit about is evaluation, and then I'll go on to more advanced work in machine translation. Okay, so here are some just illustrative translation results to have something in your head. La politique de la haine. The reference translation was politics of hate, and the IBM system said the policy of the hatred. And you kind of see that the machine translation is sort of more literal, like it's translated the la as the and the la as of the. So la got through as that in both times, where the human translator has decided that putting in la as the in the English translation isn't really appropriate in English. The IBM translation also sort of goofs by changing politique to policy rather than politics. Okay, so we get some translations out, and our question is, well, how are we actually going to look at these translations and work out whether they're good or bad translations? And up until this day, the gold standard answer to that is basically we get human beings to look at them. And, well, the problem is that model's kind of expensive. In particular, it's expensive if you're like most people in the machine learning NLP business, spending your days trying to change and improve your models to make them better. So if you have lots of money on hand, so I know for the Microsoft machine translation group, you know, they literally every week take the output of their latest research system and ship it off to an evaluation team who do human evaluation, and they just get back weekly deltas on how the system is improving or getting worse based on human evaluation. Well, that's kind of good if you're Microsoft, but that doesn't work quite so well if you're sitting doing research at Stanford University, notwithstanding the fact that everyone else thinks that Stanford University is very rich. So that's sort of led to an enormous interest in other ways to do machine translation evaluation. And I'll say a bit about that. But before I do, how do people do manual evaluation? I mean, there are various ways in which it's done. One way is just doing sort of subjective scores of how good is this sentence, 7-point scale. A common idea that's often used is this division between adequacy and fluency. So the idea there is you're trying to differentiate the adequacy of the translation, which sort of means it does translate all the content that's in the source sentence, but I don't care if the translation sounds kind of stilted, or perhaps it even put in the determiner where it would have been better, an article like that, where it would have been better to leave it out. Don't care about that. Is all of the sense of the original recoverable? That's adequacy. And then fluency is what you're producing, expressing the ideas the way that the target language speaker would, correctly using grammar, function words, and all of that kind of stuff. Sometimes people just do a simple binary good, bad on translations. I guess what that's doing is sort of, by giving a very easy evaluation task, you make it much easier for the humans to quickly evaluate sentences. The second way of doing a machine translation evaluation, this kind of parallels what we did with language models of perplexity versus word error rate, is to do it in the context of a task. So if you want to do question answering over foreign language materials, you could kind of have the internal MT component. But again, the problem is it's very hard to know how the internal components' results are kind of being reflected through the rest of the system. And so that's led people to want to try and come up with automatic evaluation methods for MT, where you can just sort of evaluate your new system every night and decide whether it's getting better or worse in an automatic fashion. And so the problem of coming up with automatic metrics for machine translation is it's kind of difficult. So why is it hard to automatically evaluate machine translation? Yeah. Yeah. So fact one is normally there are just lots of good ways to translate something. So it's not that you can say, it's not one of these tasks of here's the unique right answer, did they get it right or wrong? There are lots of possible translations, and human translators could quibble a little about whether one's a little bit prettier or more fluent than another one. But to a large extent, there are just lots and lots of translations. And in particular, as a sort of an aspect of that lots and lots of translations, normally there are lots of ways that you can order things that are okay. So, yesterday I went swimming yesterday. Both of them okay, right? So you kind of can't go through in any position by position basis. So doing word error rate for speech recognition just doesn't work doing a kind of an edit distance with insertions and deletions because there are these big reorderings that can be perfectly okay. Occasionally people have used an idea of a position-independent word error rate where you're allowed to have any alignment between the words and then you're trying to count substitutions, insertions, and deletions. But if you do that, then it's paying no attention at all as to whether you've got the right words modifying the right words, and that seems so lax. So people have tried to come up with various other ways of doing machine translation evaluation, and there are a whole bunch of them, to be honest. It's sort of become almost a sub-industry of coming up with automatic evaluations for machine translation. And, you know, there must be something like a dozen now that different people have proposed. But the original one was BLUE, which was proposed by IBM, and that's the one that I'm going to present. And, you know, the fact of the matter is this BLUE evaluation metric is still kind of just the reference point for automatic evaluation metrics. But what I mean by that is all of the other 11, the way you write your paper on evaluation metrics is that you write your paper introducing an evaluation metric and proving that it works better than BLUE. But in the real world, you know, the majority of people, the majority of the time, still compare BLUE scores, that BLUE's near enough to okay within the space of the evaluation measures that exist. Okay, so the idea of BLUE is what it's going to do is evaluate n-gram precision. So you're going to have one or more reference translations, and then you're going to have a machine translation, and you're going to say that the machine translation is good to the extent that you can find n-gram sequences which are also present in the source. And so, you know, a little bit this just seems like position-independent error rate, that you're looking for stuff here that's also there, and in some sense you are. But the crucial extra stuff that you're putting in is that you're getting a lot more points if you match subsequences. And so the idea is if you match subsequences of words with the original, that means that you're kind of capturing whole phrases correctly. Okay, then there's the stop people cheating clause, which is the final part of the BLUE measure, right? So this part of the BLUE measure only measures precision, right? So it's saying, of the stuff here, which words and word sequences can I find in the reference translation? That there's nothing in the measure that's looking at recall, saying, in the original, it says here Osama bin Laden. Does the translation mention Osama bin Laden? And that could worry you. And, I mean, different measures, some of the other MT measures do pay attention to recall. But the way it was implemented in the BLUE measure was to simply say, let's put in a brevity penalty. Because if you just had it up to here, you could totally cheat. You just take the input, whatever it is, and say the translation of that is the. And then almost certainly the word the would appear in the input and in the reference translation, and you do really well. So the brevity penalty is saying, well, you're going to be penalized unless your translation is the same length as the reference translation. Well, you'll be penalized to the extent that it's shorter. And so that sort of forces you to put words in, and so therefore you'll do better if you're putting in words that are found in the reference translation. Okay, and then I give this sort of mixed evaluation here. The initial claims from IBM and some of the initial results were that once you put in the brevity penalty, that the BLUE measure was hard to gain. That is, that increasing if you do things that improve your BLUE score, that those genuinely are improving the performance of your machine translation system as evaluated by humans. And if I sort of skip ahead and show that, there were initial results such as these ones, where here are human judgments of translation, which were separately done for adequacy and fluency, and here are blue scores. And look, you're getting a beautiful linear relationship right there. So that was the early claim. At this point, I think I have to have a big caveat to that, because in the last several years, people have started getting cleverer and cleverer at using high-tech discriminative machine learning methods of various kinds, whose only job in life is to optimize blue scores. And what people have been increasingly finding is that the correlation between blue score increases and human evaluation of translation quality has been breaking down to the extent that for the kind of increases that people are now getting in blue scores, that they're not really correlated at all with improvements in translation fluency. So it sort of seems to have really reached the point where people have to be coming up with something that is a better automatic evaluation metric than the blue score. But nevertheless, the blue metric, simply because it did give this automated metric, was very effective at driving forward machine translation for a number of years. Okay. So what you're actually doing for the blue score is that you're calculating a weighted geometric mean of your n-gram precision up to a certain n. So the most common measure that's used is the blue 4 measure, which means you're considering up to 4 grams in the measure. And you're putting a weighting here where you've got a kind of a lower weighting on 4 grams and higher weighting on unigrams. There's one very weird thing about this metric that you want to be aware of, which is that in a geometric mean, if your translation has no 4 grams that match the reference translation, you're going to have a 0 term there, and when you multiply the things together, you get 0. So the blue metric falls apart unless you have a non-zero score for each of the n-gram measures. I mean, one way of dealing that for just comparing your own systems is to say, okay, well, if I can't do blue 4, I can just back off to blue 3 or something like that. But that sort of seems a weird to bad feature of the metric, but that's how it is. In particular, a problem that raises for the metric is you kind of can't use blue scores to evaluate individual sentences, because at the individual sentence level, you might have a 4-gram overlap and you'll do really well, or you'll commonly not have a 4-gram overlap and your blue score will be 0, and it's sort of not really assessing the quality of the individual sentence. It's just kind of random stuff. So blue scores are really only sensible when done over the entire corpus of the translation, and so therefore the whole test set, and therefore you can't really sensibly say which are my best and worst sentences based on blue scores. Yes? I think the intuition is that the following. You do want to give people credit for matching long n-grams, but at the end of the day, there's a lot of luck in whether you match long n-grams, because, this one matched airport and its, even though actually it messed up and it put the there, which is ungrammatical, right? Now, the system could equally have translated it as airport and its office. And to a human being, that seems kind of equally as bad, because in both cases it's put in a the that shouldn't be there, given that the its is there, and it's only a question of which side of the its it puts it on. But, well, if it had put the on this side, it would have only gotten a bigram match, whereas because it put the on this side, it got lucky and got a trigram match. So, although you want to pay attention to higher order n-grams, it's quite noisy and there's quite a bit of luck on whether you get them right. So, I mean, it seems like, for content words that should be translated, right, that the word Guam should appear here, and if the word Guam doesn't appear here, that's bad, that seems a more fundamental fact, and that encourages you to weight the unigrams higher. Yes, you are right. Yeah, so it's kind of a compromise. I guess the bigrams still have a decent weight. Yeah. I mean, it doesn't have to be huge, but I mean, typically what's used is the order of, 500, 1,000 sentences, and enough that you could expect that, enough that you won't be getting a 0.4 gram overlap count. Yeah.
Is there some sort of like, displacement penalty? Because once you have that many words, there could be a matching word in the last sentence that really matches reference.
Sorry. No, I should explain that. Yeah, it's not that the overlap, that was something I crucially haven't explained. The overlaps, the counts of the overlaps are calculated per sentence. Yeah, so you're taking, here's a sentence and here's how it was translated, and you're just looking within that sentence for n-gram overlaps, that you can't get scores for ones that belong to different sentences or translations. Yeah, sorry. Okay, so you can run BLUE just like that by having one reference translation and one machine translation and counting up the n-gram overlaps. And people do. And so this is just one more slide that sort of shows possible outputs and sort of shows where there are n-gram matches of different sizes and gives some idea as to you as to sort of how you do or don't get lucky in terms of bigger n-grams matching. But the idea after that is, in the original version of BLUE, and still quite commonly in evaluations, people don't just use one reference translation, they use multiple reference translations. Having 4 of them is actually quite common. And the idea here is effectively, if you have 4 reference translations, you've sort of sampled the space of possible translations. So that if a human being, if a system translated something in a reasonable way that a human being might translate it, you've kind of got 4 chances for it to show up in reference translations, and then you're more likely to get higher order n-gram matches. And so people have used that idea of having multiple reference translations. On the other hand, if you think about it statistically, you could kind of think to yourself, well, that shouldn't matter. I could just have one reference translation, and it's effectively sampling. It'll still be the case that if you translate things well, more often you'll match the reference translation. And that seems to be true too. So sometimes people use multiple reference translations, sometimes they just use one. And you kind of really only have problems with using one reference translation if somehow there's a correlation between the style of a system and the style of one particular translator, which wouldn't be found with other translators. But that sort of, at this point, here's also one of the defects of the BLUE measure, that BLUE scores aren't absolute scores that you can just interpret like an accuracy score, because how high a BLUE score is crucially depends on how many reference translations there are. So that if you have 4 translations, you can quite commonly see BLUE scores in the 30s, 40s, 50s. Those are sort of pseudo percentages, 0.3, 0.4, 0.5. Whereas if you only have a single reference translation, BLUE scores will commonly be around 0.1. They might even be below 0.1 or 0.15 or something like that. And that's not meaning the system is 3 times worse. It just means you've only got one reference translation. Okay. So moving on to translation systems. Okay, so the huge part that I haven't really said anything about is, boy, how do we actually make a machine translation system? And so, in principle, this is straightforward. We've built an alignment model, probability of F given E. We've built a language model, which gives probability of E. So once we're given a French sentence, all we need to do is find the English sentence E that maximizes that product. But all we need to do is actually a very difficult problem. So doing machine translation decoding, even for the simplest models, is NP hard. And the reason for that is that simply because you're able to do these different orderings of words, right? That simply because you can translate words in any order, that even apart from the choice of how to translate a word, that's already giving you an exponential factor right there. So you end up with an NP-hard problem. Okay, so what do people do about that? People have explored some different search strategies. So you can actually do a reduction from machine translation to traveling salesman problem, because effectively the reordering of the sentence is the order in which you visit your cities in a traveling salesman problem. The problem is that you can't actually use that to translate sentences that are longer than about 5 words, because it becomes impossibly slow and complex. By and large, the technique that people use, which I'll briefly mention, is using beam search. Okay, so this is what we have so far. If you go back to the original IBM paper, Brown et al., they call it the fundamental equation of machine translation. I think you always want to be suspicious in NLP when people call something the fundamental equation of something. But as we know, it's just Bayes' rule, right? So we've got that. Is this really the best thing to use? It turns out that no, you can easily do better than that. It turns out that you can always do better by introducing yourself a hyperparameter in which you can scale the 2 halves. Simply because since the different component models, both of the component models have bad independence assumptions in them, but depending on whether one half model has better or even worse or even worse independence assumptions, that your independence assumptions always make your probability values more extreme than they should be. And so that you can effectively attenuate over extreme probability values by putting an exponent in one of the component models. Okay, so since the probability of English might be 0.001, when I raise it to the 2.4, that becomes a much smaller number, 0.0000 whatever. So if I raise a probability, if I raise the language model to the 2.4th power, does that mean I'm paying more or less attention to the language model in my machine translation? Am I paying more attention to it or less attention to it in terms of what dominates the score? I got a more. Yes, so the answer is more. And the way that you have to think about this is by looking at likelihood ratios between 2 candidates. So that, yeah, when I raise a number less than 1 to a positive power, or a power greater than 1, the number is getting smaller. But if you think of the ratios are actually getting bigger, so I'm paying more attention to it. So I did this before I came to class, so I had the numbers. So if these are with big probabilities, right? So if I have probabilities of 1/2 and 3/4, the ratio between them is 1.5. If I raise those two to the 2.4th power, I get 0.19 and 0.5. And so the ratio between them is now 2.6. And so that means I'm now actually paying more attention to differences in language model score. Okay, so that's a little parameter you can put in and improve the quality of your translation output. If you start thinking along these lines, well, maybe I can put in other factors that will improve the quality of my translation output. And here's one that's commonly used. You put in a factor that is just the length of the English translation. And the reason that this seems like it'd be useful is, all else being equal, the language model actually biases you against long translations, right? Because all else being equal, the language model score is just higher the shorter a sentence is, right? Short sentences like hello, they get good language model scores. Long sentences like, in light of current economic indicators, the Federal Reserve Board is going to meet next week and blah, 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 right? Really low language model scores. Now, to some extent, that will be catered to by the alignment model, which will want to have translations for words. But kind of it turns out insufficiently. So you kind of end up, people have found, with a bias towards too short sentences. And so you can counteract that by putting in just a factor that's the length of the English sentence, which again you can weight with a hyperparameter to prefer longer sentences. And you can do that, and it'll improve the quality of your translation output. Okay, so once you've started doing that, you start thinking, oh boy, probably there are all sorts of things I can tack on the end, and I'll be able to improve the quality of my translation model output. And that's exactly what people have done in recent machine translation work. So that people still have language model scores, people still have alignment model scores, but what people have built is effectively feature-based models of machine translation quality, where you can think of anything else that's useful, like you can just have features. A kind of a useful feature for evaluating English translations is just to look whether the English translation has a verb in it. If there's no verb in the output, it's probably bad and you're missing something. So I can simply have a does the sentence have a verb feature, and I can put a weight on that, and that will help my translation quality a bit. And so you kind of effectively then have a feature-based scoring where you can have an arbitrary set of features, and then people do things like build log linear models over these features. I'm not going to get into the details of that later. We'll come back to some of those kind of models in other contexts later. Okay. The second major idea that people have then gone to is getting away from this word-based MT. So all of the IBM models where at the end of the day it was just probability of French word given English word, context independently. And that was clearly just really bad and didn't seem like it could work very well. And I mean, in particular, if you look at real language, it's just full of all of these, what linguists often call collocations, these little sequences of words that go together. So things like real estate, note that, interested in. Note that many of these aren't conventional phrases in a linguistic sense. So interested in isn't a conventional phrase in a linguistic sense, because interested in soccer, you would say that in soccer is a prepositional phrase. This is just the verb followed by a preposition. But these are exactly the kind of collocational units that are very useful and commonplace in language. And also when you get into technical terminology, that's mainly collocations. So things like, disk drive and network router and all of those things, that they're these kind of standard collocations. And so you'd like to be able to learn those. So that was a big gap of the IBM models. And the second gap that I already mentioned with the adjective noun word ordering is we'd like to know something about syntax so we can do syntax level transformations. And so for the last few minutes of today, I'll do the phrasal translation part of that. Okay, I've done that one. Okay, so the idea of phrase-based statistical MT is that what you're going to do with the input is you're going to chunk it into phrases, whereby phrases people here just mean any subsequence of the input. No notion of linguistics whatsoever, just any subsequences of the input. And then what we're going to do is have a probability distribution over phrase translations instead of individual word translations. And so you'd have the probability that this phrase is being translated by to the conference. And so then there's still going to be reordering, which will have displacement factors in it, but the reordering will be done in terms of this phrase chunk. So effectively, the model is in some sense kind of like before, apart from rather than doing it for each individual word, you're working on these multi-word units, which are called phrases. And that's really the only new idea. But, up until the moment, essentially doing these statistical phrase-based models is the state of the art of what people do for machine translation. There's starting to be some evidence for some languages that models that try to do more with real syntax in them are better. But, this is still pretty much the state of the art, because it turns out you can just capture a lot with these kind of multi-word phrases. I will do that on the next slide. or maybe the one after. Okay. Yeah, so I'm almost there. Okay, so once we have these multi-word phrases, note that we actually are not depending on the language model totally anymore, because effectively these multi-word collocational chunks will include appropriate translations for a word inside their multi-word chunk. So we are getting kind of context-based choice of how to translate individual words. And the phrases that we use aren't of just one size, they're of arbitrary size. So that, you know, what you really do find is if there are just common utterances that keep on occurring, like your, you know, there's actually sort of formulaic prose you see in the newspaper almost every day. So you kind of have, at the close of New York trading, blah, 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 and or just learn big phrases like at the close of New York trading and how to translate them. You know, if you actually run the IBM models twice, I mean, this is really the state of the art and basically what everyone does. If you look at it as sort of a funny, creaky process, and you could think, oh, this couldn't possibly be optimal. And there has started to be a bit of research on better ways of doing things. But, you know, it really is in terms of, you know, the people who build the state-of-the-art MT systems, which I guess really the kind of the biggest players in statistical MT systems these days are Google, Microsoft, and then Southern California, ISI, and their commercial offshoot, Language Weaver. You know, this is really still what people do. You run your IBM models in one direction, English to French. And then you recall that there was this crucial limitation of the IBM models, which is that they allowed n-to-1 alignments in one direction, but not in the other direction. That seems crummy. So what you do is you run the IBM models in the opposite direction. So you get, that allows you to get 1 to n in the opposite direction. And so now you have two possible sentence alignments, and you want to merge them into a consensus alignment. And at this point, people use various heuristics. I mean, the obvious first things to think of are union and intersection, but it turns out that intersections are too sparse and unions are too dense to work well. So by and large, people are using heuristic methods with funny names like row diag final and things like that, which are doing what seems to be a sensible job of combining alignments from the two. And then this is giving you your final alignment matrix. And then effectively, you extract off all statistical phrases up to a certain maximum size, and they become your phrase lexicon. So when we go back to here, when I just glibly said foreign input segmented into phrases, the foreign input isn't uniquely segmented into phrases. It could be segmented into phrases lots of ways, but the possible ways that it could be segmented into phrases is determined by what bilingual phrases exist in your statistical phrase lexicon. So you will explore any way of cutting things up that fits inside your statistical phrase lexicon. And effectively, you're doing that in a decoder just like before, because when you translate, you're starting off with an empty candidate English translation, and you're saying, okay, I want to lay down my first statistical phrase. And so the first statistical phrase will be something in your phrase lexicon, which is some number of words of English corresponding to some number of words of the foreign language, and so you're not actually segmenting the foreign language before you begin. You're kind of segmenting the foreign language in the process of running the decoder. Okay, that's where I can get to today, so I'll stop there and be back next week and maybe say a few more minutes on that, and then we'll be going on to the next topic of information extraction.